In this video, we're going to be talking about graphs of linear equations. This is a really natural segue into kind of the visual aspect of linear equations from 2.1. And honestly, a lot of the material from 2.1 might also ring true here as well. But we're going to talk in particular about graphs. So first, we're going to discuss the visual effect of slope on linear equations, effectively like what happens when the slope changes and how does it change the aesthetic of the graph. Then we're going to be finding intercepts of linear functions. That's going to be x-intercepts and y-intercepts. Okay. Then we're going to determine equations of other linear equations given lines which are parallel, meaning non-intersecting, perpendicular, not only meaning that they're intersecting, but at their point of intersection, you've got 90 degrees. And there's going to be a different way to define this that we're going to talk about later on today. And then intersecting at a point. And what we're going to do is find that point in particular. So first, we're going to take a look at these four different linear equations. Each one of them have something different between them pairwise, either a slope or a y-intercept. And as we look at these a little bit closer, we can see their differences and what that tells us about slopes and y-intercepts of linear equations in general. So what I'm going to do first is take a look at these equations pairwise or groupwise that make themselves stick out. So as a kind of like reminder, the general form of a linear equation is y equals mx plus b. M is our slope. B is our y-intercept. So right out of the gate, just by looking at these equations, the first thing I notice is that this line is different from the others in that it trends downward. Since it trends downward, that's an indicator to me that what we're looking at is a negative slope. So when I identify the slopes of each of these equations, there's only one that has a negative slope. So there's only one line that should be trending downward, and that's going to be this line here. So this is going to be our purple equation. Okay. Next, I'm going to take a look at the y-intercepts. So these two equations both have a y-intercept at 3. Okay, perhaps respectively. But this line here has a y-intercept at -3. So that convinces me that g of x is going to be our green line. And now, what I notice in the two functions j and f of x, they both have a y-intercept of 3, which is why they both meet here. But the little bit of nuance between them is their slopes. So the red line is trending upward at a slower rate than the blue line. Since the red line is trending upward, slower than the blue line, this is going to be the slope for the red line is going to be less than the slope of the blue line. So when I consider our slopes, we've got a slope of 2 and a slope of 1/2. 1/2 is very much less than 2. So what that tells me is that j of x is going to be the red line, and f of x is going to be the blue line. So ultimately, what I want you to take away from this problem is how modifying the slope or the y-intercept of a linear equation is going to change the aesthetic. And what I really want you to take away is the difference between these two lines here. Okay, what happens if I modify that slope? All right, now, the horizontal intercept of a function is where the graph crosses the horizontal axis. So what that means is, if I look at the coordinate pair of a horizontal intercept or an x-intercept, what's going to happen is the y value or the f of x value is going to be 0. The x-coordinate is going to be our x-intercept. If you think about this from a linear equation, if we draw some linear equation kind of haphazardly, that one, fine. Here we see this is where the y equals 0. So then the x coordinate is going to be our intercept. Okay, just to make this a little bit more clear. Pew, 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 pew. So pause the video and try finding the horizontal intercept of this function. So what we're doing here is we're setting up a coordinate pair. And what I know about this coordinate pair is the y value is 0 because this is a horizontal intercept. This is going to be my y value. So here I have the equation 0 is equal to -3 plus 1/2 x. And now I'm just going to go ahead and solve for x. So I'm going to start by adding 3 to both sides. And now getting rid of this 1/2. You could think of this as dividing by 1/2, but I like to multiply by the reciprocal. It just makes things easier this way. So I'm going to multiply both sides by 2/1, or 2. And what's going to happen that's really nice is these 2's are now going to cancel. And what I'm left with is x is equal to 3 times 2, which is 6. So my horizontal intercept is going to have an x value of 6, and by default, a y value of 0. Now we're going to change things up a little bit. So first off, we clearly see that this equation is not in the form y equals mx plus b, like we'd like it to be. And also observe that we're not only asking for the horizontal intercept, which is, we'll do that in blue, which is going to be the coordinate pair something 0, but I'm also asking for the vertical intercepts, which I'll do in red. That's going to be the coordinate pair 0, whatever the y-intercept is. So we're going to need to find 2 separate intercepts. So let's start by finding the horizontal intercepts just for, familiarity's sake. So what I know here is the y value is equal to 0, and I need to find the x value. So I'm just going to go ahead and plug my y value of 0 into this equation and solve for x. All right, so this knocks out, and I end up with -2x is equal to 20. Now I divide both sides by -2. And I get x is equal to -10. Now, mind that we're asked for these intercepts, so we need to write these as coordinates. So -10, 0 is going to be my horizontal intercept. And now I'm going to set out to find the vertical intercept. So here, x is 0. And so I'm going to use the same procedure as I did before. Okay, so why did my brain stop? Sometimes that happens. So this knocks out, and I get 5y is equal to 20. Divide both sides by 5, and I get that y is equal to 4. There's my other coordinate pair. So these are my horizontal and vertical intercepts of this particular function. Now we're going to talk about parallel lines. 2 lines are parallel if the slopes are equal, or if both lines are vertical, which in that case, their slopes are still equal. The slopes are just both undefined. So if we have 2 linear functions, y equals b plus m1 of x, and g of x is equal to b plus m2 of x, the lines will be parallel if m1 is equal to m2. So what that effectively means is if we think about this from a picture, 2 lines both trend at the same rate. So 2 lines are parallel if, say, one of them, this is going to be bad, is doing this. If another line has the same trending pattern, ultimately what's going to happen is the distance between these two lines is never going to change. It's always going to be a constant. Now, what those slopes are and what those y-intercepts are, those can vary certainly. Or I'm sorry, what the y-intercepts are can vary certainly, but the slopes have to be the same in order for that to take place. So when I think about this by virtue of an equation, let's suppose I've got two lines, and we'll say m1 plus 7. Why not? We'll make this one have a y-intercept of 7. And then we'll say this one has a y-intercept of negative 11. Why not? If these lines are parallel, and the typical notation are two vertical lines, then what has to happen is when I fill these slope values in, I don't get to be too creative. If I choose some slope value here, let's say I chose, 5. Because these lines are parallel, this slope also has to be 5. Whatever I choose here, I don't have that freedom of choice here. That same value has to be repeated. Now, go ahead and pause the video and try this problem on your own. Given this line, we're going to find a new linear equation that's parallel to it, but also passes through this point. Observe that what I'm not saying that this line passes through this point. That's not true. It doesn't. But we're going to find a new equation that is parallel to the line 6 plus 3x, and it also has to pass through the point 30. Go ahead and pause the video and try this on your own first. So since I'm finding a line, the end result should be y equals mx plus b. That's what it needs to look like after all is said and done. So let's talk about the stuff that we know here. Since this line, whatever it's going to be, since this line is going to be parallel with this function f, since these things are going to be parallel, there's something I know about the slope. In particular, I know that the slope has got to be the same. So in this equation here, I discern that the slope is 3. That's the coefficient of x. So this slope is 3. Now we're off to the races. From here, I need to find the b value. So what I'm going to do is use this coordinate pair here. I've got an x value of 3, and I've got a y value of 0. So now I'm going to use this is my x value, this is my y value, and I'm going to solve for b. So I get 0 is equal to 3 times my x value plus b. And so I get 0 is equal to 9 plus b. Okay, well, what number when I add it to 9 gives me 0? Well, I could subtract 9 from both sides. I get b is equal to negative 9. So my final equation comes out to be y equals 3x minus 9. Now we're going to talk about perpendicularity. In the same way, perpendicular and parallel both have a very intimate connection in their graphs and in their equations. Obviously, this connection is going to be fundamentally different. So first, let's talk about the picture of what's happening here. Suppose I have some, that's a terrible grid. Suppose I've got this linear equation. If another equation is going to be perpendicular, what's going to happen is that they are not only going to intersect at a particular point. If you noticed, parallel lines are never going to intersect. These are definitely going to intersect, but they also intersect at right angles. If I have non-perpendicular lines, and even more generally, just if they aren't parallel, so if I've got this line here and something that's not parallel to it, these angles are not going to be 90 degrees. If they are 90 degrees, then we would do well to say that they were perpendicular, just to be as specific as possible. Now, in the same way, there's this intimate connection with their equations. So this definition is ultimately stating that if I've got these two lines, and we'll say mx, we'll say, I don't know, its y-intercept is 4. And then this line has a y-intercept of -3. Okay. Now, here's the thing. If these lines are going to be perpendicular, the notation for that is this guy here, looks like an upside down capital T. Then what's going to happen is if I choose some slope for the first line, suppose I chose 1/3 for this slope. I don't have a choice for this equation here. It has to be the negative reciprocal of the other line's slope. So this is a positive 1/3, so I know that the slope here is going to be negative because it has to be a negation. And the reciprocal of 1/3, if I switch the position in the 3 and the 1, I get a 3/1, which I would never write it like that because it's important that we're as clear as possible. So instead, what I would write is -3. Okay, so these are connected in such a way that these negative reciprocals of slope, if I choose a slope for one of these equations, the other equation, I don't get that choice. Okay. Now, pause the video and try this problem. Again, like the last one, we're going to be coming up with a line, but it has to be perpendicular to this function and pass through this point. Again, I'm not saying that this line here is passing through this point. That's absolutely not true. But I want to find a line, the equation of a line, which is perpendicular to this one, to this given function, and it also has to pass through this coordinate point. You're going to see that the procedure isn't very different. We're just going to use the information differently. Okay, so first, as with all things, I'm looking for the equation of a line. That's y equals mx plus b. Now, since I know that it is perpendicular, and this has a slope of 3, I know that the slope of this line has got to be the negative reciprocal of 3. So if I think of 3 as 3/1, its negative reciprocal is going to be a -1/3. All right, now get rid of this just for space. Now, again, I know my m, and given this coordinate pair, I know my x, which is 3, and I know my y, which is 0. So now I just need to solve for b. So 0 equals -1/3 x. Well, not x anymore, because we know what x is. It's been a long day. 3 plus b. So the -1/3 and the 3, that's really nice. These cancel out. So I get 0 is -1 plus b. And now I'm going to add 1 to both sides. And I get b is equal to 1. So that's going to be my b value. So my final equation, after all is said and done, is y equals -1/3 x plus 1. Now we're going to talk about intersections of lines. So let's think about what's happening in the picture. You notice I'm not really reading through the definitions in rigor because, I mean, I'll leave that to you all. What I'm going to try and do in these videos is provide things that aren't necessarily in the words. So if I've got two lines, that's actually a very handsome line. And I'm only saying that they intersect. I'm not saying anything about their perpendicularity in particular. I've got two lines that intersect here. So let's see what happens here. So this is a coordinate point, and we'll say this x value, we'll call that A, and we'll call this y value B. And this is on, we'll say the line y1, call this y2. Well, here's what I want you to notice. y1 is going to pass through the point A, B. Okay, now here's the thing. Something else I want you to notice. Those coordinate points that I labeled before, y2 also passes through those points in particular. So what I also know is that y2 passes through the point A, B. So in particular, both of these lines pass through this same coordinate, which means that they pass through each other. And where they're passing through each other, that's what we call our intersection. So here's what we are granted license to do with the equation because of this, which is a big deal. So let's say I've got y1 is, we'll say, m1x plus b1. And if I've got the equation y2 equals m2x plus b2, since these intersect, what I necessarily know is that they aren't parallel, because parallel lines will never intersect. So I know that these slopes have to be different. Fine. That's actually really helpful. Now, here's what I get to do. Because y1 and y2 pass through a common coordinate point, I now have license to set these equal to each other. And in this case, if I were to solve this equation, what I would get is an x value, in particular, the x value of where they intersect. So that's really helpful information. Go ahead and pause the video and find the intersection of these lines. First, I would take a second to discern whether or not there's going to be an intersection point. In particular, what I'm asking is, are these lines parallel? Okay, so here our slope is 3. And here our slope is -1. Since these slopes are not equal, then we know that they are going to intersect. So now we can find out where that is. Now, as we saw before, what I get to do is set these equations equal to each other. So let's do exactly that. And what we're going to do, we're going to solve for t. Our goal is to get a coordinate point. That's our goal. So let's go ahead and solve this equation. So first, I'm going to add t this side. It doesn't matter how you move things around. I'm going to add 4 to this side. I get 9. So I'm going to divide both sides by 4. Reduce if possible. Well, 9 over 4 doesn't reduce, so that's our t coordinate. That's great. And now here's what's really neat. Whatever this y value is, both equations are going to have that y value represented, and that y value is going to be the same. So I can plug this 9/4 into either equation. Personally, I'm going to go ahead and plug it into j of t. That looks a lot simpler to me. So what I'm going to really do here is find what j of 9/4 is. So everywhere I see a t, I'm going to put 9/4 in its place. Now I can tell just by looking at this that in order to put these fractions together, I need common denominators. So I'm going to multiply the 5 by 4 over 4. And I got a text in case you were wondering. So that's fun. So now we do 20/4 minus 9/4, and I get 11/4. And that's where these lines are intersecting each other. All right, good luck in your assignment.